Good morning. I'd like to thank everybody for joining me this morning for today's webinar on VFDs for fan arrays. We're going to discuss configurations as well as harmonic considerations. My name is Shane King and I'm an HVAC applications engineer for Yaskawa America. And this morning I do also have Tony Gabriel with me. He's going to be reading your questions as you send them in, and some may or may not be responded to via email while we go, but at the end, if I have time, we'll be taking some questions. I'll be having Tony read some questions out loud, and I will do my best to answer them. Before we get started, I want to give a brief overview of our manufacturing facilities at Yaskawa, and we'll start with our Buffalo Grove location. Buffalo Grove, Illinois. This was built in 1994, and this is where we have repair, distribution. We build our AC servo motors here, as well as our AC variable frequency drives. We are ISO certified, and if we go about an hour and a half up the road, we'll get to Oak Creek, Wisconsin. This is our other manufacturing facility in the United States, and here's where we manufacture our medium voltage drives, and we do motion and engineering panels and our HVAC and industrial enclosures. This facility was moved to this location in 2009. It was previously in New Berlin, Wisconsin. Of course, we still have all the certifications, ISO, and you can see down here in some of these images, we got a medium voltage panel here, and this is a drive panel with a low voltage drive. So if you're ordering a drive, it's built in Buffalo Grove, and we'll ship it from Buffalo Grove. But if you're ordering a configured drive, so like a Z1000 configured or Z1000 bypass, after we manufacture the drive in Buffalo Grove, it'll be driven up to Oak Creek, where we will install it into a panel. So why are we here today? We're here to understand how to apply Z1000 VFDs to fan arrays. And that's really going to cover at least the first half, probably close to even 2/3 of this presentation. After that, we'll move on to understanding harmonic distortion, why it matters pertaining to VFDs, and different mitigation options. And we'll close with the Z1000U HVAC matrix drive as the best option. Let me give you a brief overview of terms that will be used. First one would be fan array, and I would be using multiple fans to move the same air that one larger fan would move. Purposes could include going for more efficiency or redundancy. Next is VFD, which stands for variable frequency drive. I'll probably be bouncing around with different terms during the presentation, calling it a drive, a VFD. Those are probably the two main things I'll call it. Next will be a bypass, and that is as it pertains to using a VFD. So you could be running a motor with a VFD. The bypass option would be having contactors to redirect the line power around the VFD, going directly to the motor to run it right across the line. Next will be MMP, and that stands for manual motor protector. This is like a combination overload motor circuit protector with a switch on it, and I'll show you what that looks like a little bit later. And then redundant VFD package. This is going to be very similar to bypass. So if you imagine a VFD with bypass, the redundant VFD package would just have another VFD in that bypass section. So you're really just bouncing back and forth between VFDs if you're going to switch in and out of bypass. So this is a brief overview of what we're going to cover and in what order. I'm going to start out with first why a VFD, and then why a Z1000 series VFD. After that, we'll move on to different configurations of using VFDs with fan arrays, and we'll start with a VFD for each motor in the array, so where each motor has its own drive. Next would be using one drive to power all of the motors in the array, which the rest of them are going to be similar to that. Next will be a VFD with bypass to power all the motors in the array, and then using a redundant VFD package to power all the motors in the array. And there'll be different reasons for using each of these. After that, we'll kind of shift gears, move over to understanding harmonics. And as I mentioned, we'll close with the Z1000U HVAC matrix drive. So let's get started. First, we'll start with why a VFD, and then why a Z1000 series VFD. So why would we apply a VFD to a fan array? There are three main reasons, and really they're all closely related. First would be energy savings. As soon as you have the ability to run a motor below 60 hertz, you have the ability to save energy and, of course, save money. The line voltage in America, at whether it's 208, 230, 240, 460, it's always going to be pretty much at 60 hertz. And it's the frequency that determines the speed the motor is going to run rather than voltage. So with everything being at 60 hertz, if you're just running the power to the motor, it's only going to spin at one speed, the 60 hertz. So being able to vary the speed is a big deal. Next would be, with fan arrays, we're talking about a variable torque load. So when you have a motor driving a fan that's moving air, that is a variable torque load. Yes, at full speed, 60 hertz, you're going to be pushing the maximum amount of power, and you're going to be getting the most resistance on the fan blades. But it's not linear. At 50% speed, you'll be at only 25% roughly energy. So you can get some pretty good savings as you go down the scale from 60 hertz. Next would be the ability to control the speed. And like I said, these are all closely related. With the Z1000 drive, you have the ability to run between 0 and 240 hertz, and that would be in either direction. So here's a picture of the Z1000 drive. All our certification, well, not all of our certifications, but the main ones at the bottom there. So we covered why a VFD. How about why a Z1000 drive? Well, the Z1000 drive was designed specifically for HVAC applications. We're not taking a general purpose drive that gets used on rock crushers and conveyors and elevators and escalators and saying, hey, this will spin a fan too. No, this was designed specifically for HVAC applications. So the Z1000 drive, we've got it designed through 500 horsepower, has a built-in real-time clock. We have built-in 5% line impedance for harmonic distortion reduction, and we'll be covering that in more detail later as well. It comes standard with 5 kilohertz carrier frequency with dynamic noise control for quiet motor operation, and I'm going to take a minute to explain the significance of that as well. A lot of VFDs, you can run up to 12.5 or 15 kilohertz carrier frequency, and that is great for the human ear. It makes it run nice and quiet. You don't hear any whining out of the motor. However, the higher carrier frequencies are not good for the motor. Motors prefer lower carrier frequencies. They'll last longer, run cooler, and whatnot. But the problem is, once you get below 8 kilohertz, we're getting into the human ear territory, and you start hearing the whining of the motor. Well, we've developed this drive to be able to run at 5 kilohertz carrier frequency, but with the dynamic noise control that we have built in, we are still able to achieve the quiet motor operation. So this is a pretty good feature. All right, next we have several embedded communications, BACnet, Metasys, Apogee, and Modbus. And then also the Z1000 drive is available in bypass configurations, one that it transfers motor across the line at peak demand to save energy and remove harmonics. We call this an intelligent bypass. It's programmable. You don't have to use this feature, but it's a really good feature. You can set it up so that if it sees that it's running at peak demand for a certain amount of time, there's no real sense in having the drive in the circuit. So on its own, it can flip over into bypass, and now you're removing the drive and any potential losses you have in the drive, not to mention harmonic distortion that the drive would be adding into the system, and you're just running right across the line with the motor. Zero harmonic distortion now. Motor is a linear load. And the drive will still be monitoring the demand and call. So if the call or demand requires for it to lower the speed again, it'll flip right back over into drive, and it's a seamless transition. You don't see a bump in the motor or anything, and it'll take over again. Another reason to use the Z1000 drive is what we'll call exceptional design. and we do that through component derating. We'll select components that are rated for higher specifications than what the circuit really requires. Some of my buddies back in college who were mechanical engineers, they used to refer to that as when in doubt, make it stout. So that would be similarly applied here to industrial power electronics. We use the latest IGBT power modules. We have enhanced short circuit detection and self-diagnostics. The Z1000 drive, it's our first series that came out in the HVAC that doesn't need a DC bus fuse. With our enhanced short circuit protection, we don't need it anymore. And of course, inclusive power solutions. That includes our EMI RFI filter on the input, and as I mentioned earlier, our built-in 5% DC bus impedance. And we also use superior MOVs for surge protection on the input. The communications I mentioned earlier, we have the 4 embeddeds, which are BACnet, Modbus N2, and Apogee, but we also have the ability to add an option card for LonWorks or Ethernet IP. Next, we'll get into the configurations now. So the first one we'll look at is a VFD for each motor in the array. So here's what that looks like over here. We've got a 4-motor array over here, and as you can see, each one has its own drive running it. So some of the advantages here would be a motor failure is not going to take out the array. You're just going to lose that one motor. Or a VFD failure. Either way, it's just going to take out the one, and you'll be able to run with the remaining motors. But also a VFD provides complete motor protection for a motor. So when you've got one motor on the output of a VFD, that VFD is better than an overload and fuses combined. Next, you do have the ability of individual control of those motors if you needed it for any particular reason. Cons, it could prove in some cases costly to provide a VFD on each motor in your array when you're doing an array. It does get done, but it could be costly. This is kind of a lesser con, but I still bring it up. There is a potential for nuisance over voltage faults. If you end up having a VFD having a call for lower speed than the rest of the motors in the array, that air that's moving through is going to be trying to overdrive that motor that drive is running, and that'll result in an overvoltage fault. Another thing to consider would be mounting space. So again, if you're using a VFD for each motor in the array, you do have to have a place to mount these VFD packages. Over here on the right, you see we've got 4 E7 packages running a 4-motor array. And in this particular case, they did have the mounting space, so they had enough real estate there to mount them, and it looks pretty good. But you do need to run separate power and control wiring for each VFD, so that could start getting you into a little bit of trouble. It could get messy. Let me back up here. Especially with the output. I mean, you're running separate input power to each VFD, but the output power definitely has to be separated. If you're using multiple VFDs in an array, each one has to have its own output conduit run to the motor that it's running. They cannot share output conduit. Whereas if you do it with one VFD, those motors can all share the same conduit from the output of the drive to the motors. And of course, the more wiring you got to have, the messier it could get, putting money in for electrician hours and whatnot. Alright, so let's move on to looking at using one VFD to power all the motors in the array. And over here on the right, we've got a depiction of the same 4-motor array, but now we've got one VFD powering it. One advantage, of course, is now you're minimizing the amount of panel space that's required for the VFD. Simplified wiring, you get your power in, power out. You can share the same conduit out to those motors from the output of the one output of the VFD. Now you're definitely going to have a uniform speed now for your fan array because that VFD is going to be putting out the same frequency. So as long as you've got the same motors, they're all the same and not different RPM, same frequency is going to be running them all at exactly the same speed. And now one motor failure is not going to take down your whole array because you could still just run the remaining motors. And the VFD can do just that. It'll run the remaining motors, and it can run them at a higher speed if necessary to meet the demand. One of the things you do have to consider when you're using a VFD to power all the motors in the array is that with the sharing of the VFD output, each motor is going to require its own overload protection. Because the VFD, it only sees one load on its output. So now you do have to individually protect the motors. So you got to have overloads, an overload for each motor, and then fuses, the fusing for short circuit protection. And a means to remove an overloaded motor from the circuit so that you can still run the remaining motors. So this would be fuses, contactors, and overloads. Now, in some cases, you can replace that with MMPs, the manual motor protectors I mentioned earlier. And that can take care of the overload protection. These are, like I said, manual motor circuit protectors, and they're able to open up the circuit now. You don't have to have contactors. So under what conditions can we use the MMPs in lieu of the fuses, contactors, and overloads? Well, number one, you do want to have a circuit breaker or fuse disconnect upstream for branch circuit protection. And there is a limit to the number of motors in this arrangement, and it is horsepower dependent. And it's horsepower dependent with the the number limit too. So based on the horsepower, you can have so many motors and so on. We're not going to get into the details on that. That would be probably a whole presentation somebody could put together. Downside, in this configuration, we do have a point that would be considered a single failure point. Highly unlikely with a Z1000 drive, but schematically that's what it is. A VFD is a single failure point in this configuration. So if you do have an issue with the VFD, a fault or a failure of any kind, you do have a potential of your entire array going down. So let's look at an option for that. How about a VFD with bypass to power all the motors in the array? Over here on the right, we have just that. Depicted here, we've got a drive. In this case, it's a 3-contactor bypass, circuit breaker upstream here, and we've got a 4-motor array with MMPs. So now we have a backup means of running the motors when the VFD is down. This right here would be the bypass contactor. But in this situation, now that we have a means of running the motors without the VFD, we're going to have the line power going directly to the motors. So we do need to provide short circuit protection for when running the motors across the line in bypass. So there we have our fuses. We can add them there, right upstream of each motor circuit. Or we can have them upstream in the package. So we could add the fusing right after the breaker or use a fused disconnect. I was able to find an example of a Z1000 package set up for running a 4-motor array out on the shop floor in production. This was fresh from production and it was pretty much ready to go. I think this was coming out of test and they were getting ready to ship it. So we'll take a look inside here. Right here we have a Z1000 drive. It's a 50 horse. Right here we have our fused disconnect input. Here's our, in this particular example, this is a 3-contactor bypass, so we've got our 3 contactors here. And right here we have our 4-motor array. These were 4 10-horsepower power motors, and notice we are using MMPs in this configuration. It makes it pretty neat and tidy. So let's take a look at redundant VFD packages now to power all the motors in the array. And first, one question some of you might have is, what exactly is a redundant VFD package? So we're going to show kind of schematically over here what it looks like. This would be what I would consider a generic run-of-the-mill redundant VFD package. So we've got a disconnect switch here as the main power for the enclosure, and then we've got VFD-A, VFD-B, and each one of them has its own fused protection on the input. And down here we have our isolation contactors, so that when we're running one drive, we're not backfeeding power into the other. And of course there's one motor in this particular example that they'd be running. That's because this is just a standard redundant bypass package. I was able to find one of those out on our shop floor as well. So here's a look at the outside of a redundant Z1000 bypass package. You can see we've got a keypad here for each drive. We've got drive A and drive B, and then we've got a little control panel section here with some LEDs and switches, and we're going to zoom in on that and take a closer look at them. We've got our fault annunciation lights here, so you can see if drive A is faulted or drive B, or if we have an external fault like a freeze stat or even an overloaded motor. We've got run status lights here, so we know if drive A is running or drive B. And down here is our switches for control. So right here, the fault transfer switch is where we can tell the package how we want it to react on a drive fault. If we have it over here in the manual position, then the drive will be faulted and it'll be waiting for you to tell it to run the other drive. Or we can have it in auto. So that way if the drive is running and it does fault, it'll automatically switch over to the other drive. Next we have our HOA switch, and of course that would be related to whichever drive may be running at the time. You have your full handoff auto control. Then over here we've got our drive A, drive B switch, so this gives you ability to walk up to the unit and run it in drive A, or have drive B run, or just have it in the auto position so that your remote controls can be controlling the package. We'll take a look inside of this. In this example, we've got two 40 horsepower Z1000 drives. In this example, it's a circuit breaker rather than a disconnect switch. So here we have our input circuit breaker. And we've got our fuses for drive A, input fuses, and we've got our input fuses for drive B. And now we're gonna kind of zoom in and we're gonna look at the isolation contactors. And here they are, the isolation contactors for drive A and drive B, K1 and K2. And now we're going to kind of shift towards the upper part of this photo to look at the rest of the components. Here we've got our ice cube relays for handling the logic for switching between the drives and handling faults and control. This would be our terminal strip where the customer can land their control wires. And our step-down transformer to make it all work. And then we've got our motor terminals. So let's take a look at the redundant VFD package now running a 4-motor array. Well, not running, but a configuration for it. So here we've got our disconnect switch, we've got drive input fuses, we've got our isolation output contactors, and we've got our 4-motor array. And in this example, we're using MMPs. So a pro would be, what happens if we lose a VFD or we get a fault? A VFD failure is not going to bring down the system. It's just going to switch to the other VFD. You're still going to be running your 4-motor array. Okay, what if we lose a motor in our array? Well, now we know that one motor failure is not going to bring the system down. and we can still run the remaining motors in the array, and the VFD can compensate however necessary to make sure we're still maintaining flow. One question some of you might be asking would be, what is the ideal fan quantity in an array? And as you could probably guess, I'm not going to have a direct answer to that question. But I can tell you it's really going to be determined by whatever your reason is for using an array. There could be more than one. I mean, one reason could potentially be for efficiency. Some believe that they can achieve better efficiency with several smaller motors than one big one. The jury might still be out on that, but that is one school of thought. But redundancy, that could be really a big reason, and what I would consider a main reason for the redundancy. You could have a critical operation where it's controlling the ventilation in an operating room in a hospital. So I could see redundancy coming into play there as the main reason. Another question would be, does the motor protection have to be built into the VFD enclosure? And the examples we've shown so far, that's what it's been. That's what I've been showing you so far, but no, it does not necessarily have to be in the VFD enclosure. As you can see, this handsome fellow on the right is looking at a motor array panel with 8 MMPs. So this is a system that's running an 8 motor array, and if the camera were able to pan over to the left, you would see a Z1000 redundant bypass package. So it's just a standard run-of-the-mill redundant bypass, and they did their motor protection externally. Circumstances will dictate, of course, direction, but you can save valuable space in the VFD enclosure if you are doing the motor protection panel separate. And of course, you could also save money without having to have it custom engineered in the VFD panel for however motors you need and what their horsepowers are. That pretty much covers the array detail so far of this presentation. So I'd like to shift over to understanding harmonics. Don't be intimidated by this slide. I just want to be able to cover some conventional drive topology to be able to broaden the understanding of how this all works. What an AC drive does is it converts AC drive to DC, and it does that through this input rectifier here. So we've got a diode module where we take our 3 phases of input power and we rectify it into DC. So if you've got, say, 480 volts on your line, it's going to get rectified to DC. So our DC bus now is going to be sitting here around maybe 660, 670 volts DC. And then remember, as I mentioned earlier, the line voltage in America is 60 hertz. So it's only one speed then for an AC motor. And we need a way to change the frequency. So by doing this, converting it to DC, we can now use IGBTs here on the output to recreate a waveform to go out to the motor that we will now have full control of what the frequency is going to be. We've got the 670 volts to work with, so what we've got to do is make kind of a square wave out of our sine wave, because the voltage is, with it just being one voltage, we're going to be able to make a square. We'll have putting out pulses of voltage in the positive direction and then in the negative direction to create our sine wave, and we call that pulse width modulation. I'll show you that in a second here. So the advantages to this process are control and energy savings, and you get a good displacement power factor. And with VFDs, they are a pretty compact size now. Over the past 25 years, they've been able to get pretty small. Disadvantages, of course, are going to be poor input harmonics and poor distortion power factor. But let's take a look at that pulse width modulation I was talking about. Here's a depiction of the pulse width modulation. With the IGBTs, we're able to pulse the voltage here in the positive direction to make a square wave, and then here, again here in the negative direction to make a square wave. the key here is we're trying to get the motor to draw a sine wave of current. And we are able to control that. The width of a pulse is actually the time duration of a pulse. So on the edges of the square, we've got shorter pulses, which will result in a lower current draw. But here towards the middle, we'll have a longer pulse. The longest pulses are in the middle to give us a high current draw. So even though we've got a square wave of voltage, we're able to get a sine wave of current to go out to that motor. Now the problem is, as these pulses are created, that goes back through the VFD and back out onto the line voltage, and that's where you can get your distortion. So what is harmonic distortion? I'm going to read we'll call it the clinical definition here for you. Harmonic distortion occurs when a nonlinear load draws current that is not perfectly sinusoidal and creates multiple integers of the waveform's fundamental frequency. So let's take a look at what that looks like. You know what, before we look at that, we're going to look at this. This is what the current waveform looks like with a linear load, and a linear load is going to be just a three-phase AC motor drawing power right from the line. This is what your current waveform is going to look like. It's a nice, beautiful sine wave. But if we put a VFD in between the line voltage and that motor, and we run the motor, now our sine wave of current heading into the VFD is going to look like this. I mentioned the integers of the harmonics. So here we've got the 9th harmonic, 7th, 5th, 3rd. Each of these gets added onto the fundamental frequency that you've got. In this case, it's a 50 hertz example. That was the closest I could find. But when they all get added on to that sine wave, this is what you get. This is what it ends up looking like. So that's why harmonic distortion can be a problem. So why does it matter? In many cases, it's going to matter to you because you need to meet IEEE 519. Current distortion results in conductor heating. It'll affect the sizing of transformers. If you've got your transformers sized properly, but you don't account for harmonic distortion, or you didn't know you were going to have it, now you're going to have transformers overheating. You could have larger utility bills and then possibly even fines. So IEEE 519, what is it? IEEE recommended practice and requirements for harmonic control in electric power systems. IEEE had to come up with a standard to try to control the amount of harmonic distortion that's acceptable. So they came out with this standard in 1992, but since then it did get revised in 2014. The major difference between these two standards, I mean the most relevant, is going to be the point of common coupling, which is the PCC, and that's the point at which you take your measurements to determine whether or not you're in compliance with IEEE 519. So a little comparison here between the standards. In the 1992 edition, it was a 101-page teaching document with the point of common coupling vaguely defined. I don't believe it was intentionally vague, it just worked out that way. It ended up being interpreted to be device focused, which is not the intent, and it covered short-term measurements. So they cleaned this up. They decided they wanted to straighten everything out in 2014, so they reissued it as a 29-page document with no attempt to educate. 12 of those pages are introduction, disclaimers, participants. 7 of them are annexes. It's boiled down to 10 pages of actual content. Even I could probably digest and understand the 10 pages of content. The main thing gained here, of course, was the point of common coupling was more clearly defined, and they put more stress and emphasis that this is a system-focused standard, not meant to be applied to individual components. Here's kind of a visual example of how it was viewed, how the PCC was viewed in using the 1992 standard. So you've got your your secondary side here with the transformer feeding your facility, and we call that the PCC, point of common coupling. Well, as you can see, the way this is depicted electrically, these are all the same points. So we ended up having specifying engineers and consultants and whatnot defining the point of common coupling at the terminals of each of these items, especially at the terminals of VFDs, which really was not the purpose of the standard. Here's an excerpt from the 2014 document, and I'm just going to read this to you. The recommended limits in this clause apply only at the point of common coupling and should not be applied to either individual pieces of equipment or at locations within a user's facility. IEEE 519 really doesn't care what kind of distortion you're seeing at a particular point in a mechanical room or somewhere else. Here's a depiction of what the standard looks like now. I showed you the one, let me just go back here, what it looked like with the 1992 standard. Here's a better depiction now with the 2014 standard. What they're saying is, here's the public power supply, and they're feeding Shop A, Clinic B, and Bank C. Their main purpose is they want to make sure that the harmonic distortion that Shop A is feeding into the line does not affect the sensitive equipment that's over here running in Clinic B or in Bank C. Variable frequency drives are neither compliant nor non-compliant with IEEE 519. And also, they're not the only producers of harmonics. A VFD is a nonlinear load, but really anything converting AC to DC is a nonlinear load. Copy machines in the office, printers, your computers, those are all nonlinear loads. It's part of a larger user's system, so compliance needs to be measured at the point of common coupling. And harmonics estimation software is available for doing that. I mean, if you know the VFDs that are going to be hanging off of a transformer, you can run a harmonic calculation with free software. Most of the major VFD manufacturers do provide that software free on their website, and I know Yaskawa does as well. The main purpose for IEEE 519-2014, and this is another excerpt out of their document, is this recommended practice is to be used for guidance in the design of power systems with nonlinear loads. So let's take a look at mitigation. I mean, we've covered harmonics, harmonic distortion, what it is, but now what can we do about it? So we're going to look at a few of those methods. One would be a DC reactor or a DC link choke, which adds impedance to harmonic frequencies. Passive harmonic trap filters. Multi-pulse rectifier inputs, so that would be like a 12-pulse input, 18-pulse input. And then there's active front-end VFDs. And low harmonics VFD design, which would be an AC to AC design, creating sinusoidal current. It's kind of skipping the whole DC bus phase of the situation. One thing all of these mitigation options are going to have in common is they do cost a little bit more money. I mean, if you think about it, your cheapest solution on a drive is going to be a straight 6-pulse drive that doesn't have any harmonic mitigation. So you do things to add harmonic mitigation, you're going to be adding some cost to the system. And it could reduce efficiency as well. We're going to compare 4 of the major harmonic mitigation options. And the first one is going to be looking at, well, the first one isn't an option at all. We're going to look at what harmonic distortion looks like with just a 6-pulse VFD that doesn't have a DC bus reactor, no harmonic mitigation added to it whatsoever. What is our starting point? And this is it. This is what your current waveform looks like, the distortion. So a VFD that has no harmonic mitigation applied to it is going to have up to 88% current distortion with a power factor of 0.75. So what happens if we add a DC bus reactor? Here, just by adding a DC bus reactor, we're getting that current distortion down to 33%. That's a massive cut from the 88%. And we've got a 0.90 power factor. Every Z1000 drive has a built-in 5% DC bus impedance. So you're not paying extra for it, we just have it built in. We're already getting you down to that as low as 33%. You're going to be in the 30s range for sure. Now let's look at another popular option. That would be adding multi-pulse, 12 or 18 pulse to the circuit. So with 18 or 12 pulse, we can get the current distortion down to 6 to 12%. That's another sizable cut in our distortion, and we can get our power factor up a little bit higher. Now we've got it up to 0.95. It's come a long way, this waveform, from the one up top, so that is pretty good. But I did mention earlier I wanted to show the Z1000U HVAC matrix drive as the best option. So let's take a look at that. Here it is. That's a pretty clean looking sine wave there. With the Z1000U drive, which is an AC to AC drive, we now can get that current distortion down to 3 to 5%. And the power factor up to 0.98. So let's take a look at that. Let's look at the Z1000U HVAC matrix drive. And there she is, smiling at us. The Z1000U HVAC matrix uses bidirectional switching with IGBTs. So as you can see here, it's like two IGBTs kind of interposing one another. This allows bidirectional switching now, and we're able to produce a simulated sine wave output. And it also has regenerative capabilities. So no more of those nuisance DC bus overvoltage faults. Any energy that's put back into the system from the motor, instead of having to burn it off as heat through a dynamic braking resistor or anything like that, it just doesn't get used, that's all. So it saves you money. The Z1000U matrix drive uses 9 of these bidirectional switches, and you'll notice there's no DC bus. If we compare this to that conventional drive topology slide I showed you several drives back, this would be the apples to apples of what the drawing would look like of a Z1000U HVAC matrix. So we've just got our line voltage is coming in, it's hitting these bidirectional switches and being switched out to the motor. No more DC bus. So advantages are ultra low input harmonics. We've got a near unity true power factor now. I showed you that was 0.98. We've got the regenerative energy savings, and this is also a smaller solution than other of the comparable harmonic mitigation solutions, like 18 pulse. The price is comparable as well, and it's going to be, in most cases, less costly than going with 12 pulse or 18 pulse. A little bit more on the theory of operation of the Z1000 drive. Z1000U HVAC matrix. At any given time, it knows what the voltage is on any of the 3 input phases. And it's going to be different on each of the 3. So it can pull any voltage it needs from any spot on the front end to create the output voltage waveform going out to the motor. Here's a depiction of comparing the Z1000U to what could be argued as the other best option, and that would be 18 pulse. So over here on the left, we've got our current distortion, and on the bottom, we've got speed from left to right. The blue line is 18 pulse, green is Z1000U, and as you can see, there's no point on the line where green is higher than blue. High is bad, low is good. See, we got our distortion over here on the left. One common level that's referred to a lot, you see it in a lot of specifications, is 5%. We want to be under 5% total harmonic distortion or current distortion. Well, with the multi-pulse, 18 pulse, for instance, we've got to be up to 90% speed before we're really achieving that 5% or less harmonic distortion. But with the Z1000U, we can be as low as 65% speed and get below that 5% threshold for harmonic distortion. So let's do a little reality check here, what that looks like. Over here on the right, we've got a 75 horsepower bypass, 3-contactor bypass, with an 18 pulse input. So here's our drive, 75 horse drive. Got our contactors here, 1, 2, 3. 18 pulse transformer and all the associated reactors and rectifiers and fuses that go along with it. And this is a pretty big enclosure here. I mean, obviously you see here it's a floor mount enclosure. And over here on the right, we've got same thing, 75 horsepower Z1000U matrix bypass drive, 3-contactor bypass. This package over here on the left is doing everything the package on the right is doing, except it's doing it better and cheaper. And this is to scale, by the way. This drawing on the left is to scale to the one on the right. So can this technology be applied to redundant fan array packages? And what would be the benefits? Well, I've already shown you that it is better, and it's also smaller, and it is cheaper. I don't like using that word. It's less costly. So let's take a look at what this looks like. We're going to do this one more time. Over here on the right, we've got a 50 horsepower, 18 pulse redundant VFD package. So we've got 50 horse drive, 50 horse drive, 18 pulse transformer, and oh, what's this? Yep, another 18 pulse transformer. When you're doing these multi-pulse inputs on drives on a redundant VFD package, each one has to have its own 18 pulse transformer input. So that puts us into a very large enclosure. How big, you ask? Well, this particular one, 66¼ inches wide and 84 inches high. This is a walk-in closet. Can we add a 4-motor array? I will concede that point. We could fit a 4-motor array in this enclosure without increasing the size. There's room in there. It'll fit. But what if we do this with Z1000U HVAC matrix? And, of course, what would it look like? There it is. Here we have on the left Z1000U redundant package, the 50 horse redundant package for a 4-motor array. And in case you don't believe me, we'll take a look inside here in a minute. This is 62½ inches high, 36 inches wide, and it is a wall mount enclosure. This is a real world example. This exists. We built this. So here it is, 50 horse redundant Z1000U drive, and we've got our 4-motor array built in here. So this package on the left, once again, is doing everything the package on the right is doing, but it's doing it better, and it's doing it for less money. So what we covered today was why a VFD and why a Z1000 VFD. A drive for each motor in the array, using one drive to power all the motors in the array, drive with bypass to power all the motors in the array, and using redundant VFD package to power all the motors in the array. Then we covered a little bit on understanding harmonics and the Z1000U HVAC matrix. And that's all I got. I think we have a few minutes left here, so I think I can take some questions. And
yeah, we do have a few questions that came in. I'm just going to ask Shane to mute the mic, and we'll discuss, and then we'll answer some of these.
All right, I'll be right back. And we're back.
Okay.
I'm going to have Tony ask me these questions, and I'm going to either answer or deflect. All right, Tony.
Right. So we had a question asking for comparison for our standard AND cabinets, where we run 2 motors to an array.
Okay. The difference between an AND package and an array package, it's pretty basic. In the AND package, we have the overloads run in series going back to the motor, back to the drive to fault the drive, because in the AND package, we don't have individual contactors that we can open up to drop one motor out and keep the other motor running. So in an AND package, if one motor overloads, the drive will fault, and you're done. You're not running anymore. Whereas with an array, we have it so that we can open up a contactor for the one motor and continue to run the others without faulting the drive.
Okay. And then options, input options. So let's say they wanted a bypass. Can you get a service switch maybe an input option like that, or a bypass soft starter?
Yeah, yes to both, actually. Those are, in some cases, custom engineered. So if you're looking at a selection and you want service switch and you don't see it as an option, or you want soft start bypass and you don't see that as an option, we do quote those. We just have to quote it as engineered. So we've got usually a 1 to 2 day turnaround. We'll be able to get a quote back to you on a price.
Okay. And here's one. So if you had long lead lengths, typically we would implement a DVDT filter or maybe an output reactor. How is that configured on a fan array?
I would think in most cases, for sure, you can have an output reactor on the motor. As far as DVDT goes, I would have to get back to you on that. So whoever sent that question in, go ahead and send your question to me. Email it to me at shane_king@yaskawa.com there, and I will get back to you with an answer.
Okay. And then time from quote to finished product for engineered arrays.
Okay. Well, the quote process, as I mentioned, maybe 1 or 2 days. As far as finished product, I won't count the time in between sending a quote to you and getting a PO from you. So we'll say it'll take 2 to 3 weeks. You probably want to get submittal drawings first before you approve. So we're going to go, say, 3 weeks to getting your drawings. And then once you approve, then we'd be looking at 6 to 8 weeks probably on most custom engineered packages. If it's Z1000U HVAC matrix, depending on stock, it could be that, or it could be 8 to 10 weeks, somewhere in that ballpark.
Okay.
It really is a case-by-case basis, though.
All right. And here's a question regarding 18 pulse versus matrix drive as far as pricing.
Okay.
So advantages, what is cheaper or a better alternative as far as pricing?
Well, I think right out of the box with our standard pricing, you're going to be able to get Z1000U matrix packages at a lower price, lower cost than 18 pulse. This is just a personal opinion. I don't know why anybody would be buying 18 pulse anymore.
Yeah. And we can run a harmonic analysis. Building automation runs harmonic analysis to see if you actually need multi-pulse or Z1000 matrix drives.
Yes, as long as you have the information on the system that we need, transformer that the drives are going to be on, and that nature, we can make sure that you're not having to buy more harmonic mitigation than you need. We'll get you just right, just what you need.
Yep. Okay, that looks like it wraps it up for questions. We're probably going to mute the mic and we'll be on for another 5 minutes. Anyone else have any more questions, just send them in and we'll address them here in the next few minutes.
Okay, it doesn't look like there's really any more questions coming in right now. So we're going to wrap this up. Keep in mind, any questions you do have, you can send them to me, Shane_King@Yaskawa.com. And everybody, enjoy the rest of your day and the rest of your week. Thanks for listening. Bye.